Okay, I think we'll get started. So this is the first lecture of the Introduction to Physical Chemistry 2 course. And as I mentioned in the introductory video, we're going to be focusing more on macroscopic systems. So for the most part, we'll be looking at things that we can hold in our hand and utilize in the laboratory. And we're going to start off our discussion with energy and work. But before we do that, let's talk a little bit about the types of systems that we run into. And we mentioned some of this in Introduction to Physical Chemistry 1, but here we will start to handle the difference between a conservative system or a non-dissipative system, which is primarily what we used all the time in the first course, and now talk about both conservative systems and non-conservative systems or dissipative systems. And these are going to be systems that interact with their environment in some way. And the ways we're most familiar with are through friction or drag, but also through the dissipation of heat that's developed in a chemical reaction or some other internal mechanism. And so we want to start to think about not only the system itself, but its surroundings and its environment. And so we'll start with that. We'll start talking about that even today. All right, so let's talk about energy. That's a great place to start. And so let's imagine we have this ball on this slab, concrete slab, for example, and the ball is going to fall off and land on the ground over here. So from the ball's perspective, it has lost some energy. It has been at a point of higher potential energy, and now it's at a point of lower potential energy. But the ball is sitting still on the ground here, and so it has no kinetic energy. And so the total change in energy, the total energy has to have changed. It changed by the amount of the change in the potential energy, because it had no kinetic energy up here, has no kinetic energy sitting down here. Now, during the flight of this ball, and the instant it hits the ground, that system is a conservative system, as long as we're ignoring the drag due to the air, and it falls, and the potential energy has been converted to kinetic energy, and the instant it hits the ground, the entirety of that potential energy has been converted to kinetic energy, and the system is behaving with conservation of energy as we would expect. Now the ball hits the ground, and there's the interaction with the surroundings. So it might make some sound. That sound carries away some energy. It causes vibrations in the ground that ends up heating the ground, and the energy is dissipated out into the ground and into the ball as heat. And so we can have a change in total energy if our system interacts with the surroundings in some way. Now, collectively, the systems and the surrounding conservation of energy must hold, because as taken as a total unit, that has no external interaction with anything, so it itself is a conservative system. So when we think collectively, that is helpful, because any energy we lose or gain into the system that we're thinking about, we can see that coming from the surroundings or going to the surroundings with exactly that same amount of energy. And that's how conservation of energy works in these dissipative systems. Okay, well, now let's talk about work. And work is defined, an infinitesimally small amount of work is defined as moving an object through a force, or against either with a force or against a force over a distance x. So it's a force times a displacement. This has units of newtons times meters, but that itself is units of joules. So work is a form of energy. Now, we don't do calculus in this course, but if we want to work this up to a macroscopic amount of work instead of just an infinitesimal amount of work, we can write this as this is what the work means, and so we have this integral. Now, if the force, and this is going to be from x1 to x2. Okay. Now, if the force is constant, we can pull that out of that integral, and I'll do just a little bit of calculus here. And we see that the work is the force times the distance we've moved from start to finish, because this is the final spot, and this is where we started. We started at x1, moved to x2. Now, often the force is not constant, and then we're stuck. We would have to do some calculus. We'd have to know what the formula for force is as a function of position. Which we could for like a Coulomb's law or something like that. So even to do a Coulomb's force, we would need some calculus. So most of the problems in your book, if you didn't pick up a calc-based physics book, will involve constant forces. Okay, so this is how work is defined. And so let's see that happen in action over here. So let's move the ball from here up to here. Now, what is the ball experiencing? So it is, we are moving the ball against the force of its weight. The weight force is on the ball. And so we have to provide, so we're going to be an external force, is going to provide that amount of, do that amount of work to get the ball up here. So the work done by the external device, let's say it's us lifting that up there, is going to be force times the height. We're lucky because the weight force is constant. So that's an example where it's constant. The weight force is mg. And so if we call this distance h, then the upward force is Fh, and F is this. Now, let's say we take and we carefully lower that down and set it on the ground. We're not going to push it off and drop it off. We're just going to carefully lower it on the ground. Then the work is minus Fh. Now, what does the minus mean? That means the work is being done on us. The system here is doing some work. Now, this brings up something that's going to be a little bit unfortunate for us because we're kind of simultaneously learning chemistry and physics. That is basic, that's a convention, a decided upon convention, that when the system does work on us or on the environment, it's negative, and when the system does work, when we do work on the system or the environment does work on the system, that's positive. That's typically known as the chemist's convention. So if we go on further in our physical chemistry, we're going to run into that situation where work is defined as negative if the system does work, positive if the system has work done on it. Unfortunately, the physics perspective or the physics convention is flipped. And so it's likely that your book will have these signs changed, and the problems that you'll be working on might be oppositely signed. So what I really encourage you to do is think about the physics rather than following your nose on the sign. Decide on a convention, right? Your physics book will have the convention that if the system does work, it's positive, and if the surroundings do work on the system, it's negative. We're going to be working with the opposite system here through this course, and thus just be careful with that and know what's happening. That's the most important thing. Are we doing work on the system? So did the system go from a lower energy state to a higher energy state? Or is the system doing work on us? Did it go from a higher state to a lower state? Again, that's convention. Okay, Now, let's take both steps together. So we put the ball up, take the ball down, and the total work then is going to be 0. Now, all this while, we have implicitly assumed that we are working in a otherwise conservative system. And in that case, then it doesn't matter how we set the ball on top or put the ball down. What we will discover when we're working in dissipative systems is that it does matter. It will matter how this is put up and how it's taken down. So the pathway through which the system is changed will be important. But in the early problems that you're working on, in whatever physics books you have, that won't be the case here. And that's due to the system being otherwise conservative. Okay. So the energy was first provided by something, us. We lifted it. And then it was given back by the system back on us. So let's do a quick example. Let's say we have a 15 kilogram mass, and we're going to lift it and put it on top of a 1.5 meter slab of concrete or something. So the force necessary is going to be the 15 kilograms times the acceleration due to gravity. So that's going to require a force of 147 newtons. Okay, so the object is facing 147 newtons of force, and we're pushing against that. All right. Now, the work then will be this external force times the height. Well, our height we said was 1.5 meters, so we're going to take the 147 newtons times 1.5, and we get 221 joules, or Newton meters, joule. So there's an example of the work that we've done on the system. Now notice I've used the positive convention here. A problem like this, most likely in whatever physics book you have, would have a negative convention. And where that would come from was this force is downward, the acceleration is downward, and that's where the negative sign would come from. So we've used this chemist's convention here. All right, well, let's take a little more nuanced approach to this and set the stage for important concepts to come involving thermodynamics. And work will be a very important part of thermodynamics, as will heat. And we'll see both of these coming in. We already saw it over here, that when this went thud on the ground, it gave its energy to the ground as heat. So let's look at a system where we've got our whole thing in some kind of insulated chamber. So it's completely isolated from the outside world. That's called an isolated system for obvious reasons. And let's say this is just teetering on the edge, just balancing. Right? So the trouble with the sort of conceptual problem with a totally isolated system is how do you get it to do anything? Well, let's imagine this is sitting just teetering right on the edge and then just falls off. And so this brings up the idea of what's called a spontaneous process. In this system, this isolated system, this ball will spontaneously fall to the ground. It will not, if it's laying on the ground, come up to the top. So it will spontaneously fall to the ground. In doing so, we're a totally isolated system, right? Therefore, our total energy must be zero, right? Because we are not connected with the outside world. But we land here, and our kinetic energy is zero, but our potential energy has changed. It's not zero. Right? So we've lost potential energy. And so what that has done is it has gone into vibrations of this chamber, of which nothing can come out. It's totally insulated, so we can't have anything escaping here. But these have now, so because of the collision with the ground, that has been dissipated into heating up the system. And so we'll call that Q internal. So that's going to be the internal heat. And so what must have happened to this system is that its temperature before and after the ball fell must have risen, because there's no way for this heat energy to escape. All right, so that's an isolated system. Let's make something called an adiabatic system. We'll keep this same insulation. We'll just poke a small hole to attach a rope on a pulley system and make some kind of crazy contraption here so that when the ball falls, it will lift this bucket. And if we still have our 10-kilogram ball here, let's think about spontaneous process, or so-called spontaneity. This is just teetering here. This will fall, right, spontaneously if the bucket weighs less than the mass. And let's take the example of 1 kilogram here in the bucket. So for state 1, we're up here and the bucket is down here. In state 2, this has fallen to the ground and the bucket has raised. So let's see what happened internally and externally. So the external work is simply what this system did to this bucket. So in a sense, we're lifting this bucket up to this height. Right? That's like us lifting the ball. This is playing the role of us here now. So, well, we'll be careful there. This is the system we're interested in. Here's some external environment. So this system is going to be doing work on this external environment. And so this is going to be just, and let's give this a height here. Well, yeah, let's say this is, let's do our 1.5 meters. So what's happened here is the work is now M, 1 kilogram, G, which is 9.8, right, times the 1.5. Okay. And that's going to be 22.1 joules of work. Now, what happened internally? This has fallen spontaneously, and if we look at the change in potential energy, delta, I guess potential energy V, we're going to kind of go back and forth here, and I'll probably make this mistake a lot. Potential energy V or potential energy U, we're going to run into cases where neither of those letters are very good. All right, so now let's look at our change in potential energy. That's just going to be 10 kilograms times 9.8 times the 1.5, which is the 221 joules. And so what's the difference here? The difference is this is heat that went into this system. Just like up here, this is like falling and raising no bucket at all. And so we're going to get the heat internal to the system is going to be 221 minus 22.1 joules. So our temperature before or after is going to be greater than our temperature before. Now, yeah, so now let's think about the case where we do a little more work, right? So let's put 2 kilograms here. All right, so let's go ahead and put 2 kilograms there. When we put 2 kilograms there, this will still spontaneously fall, but what's going to happen? This 2 will come down here, right? And so that will be a 2. And this will be 44.2 joules. So that means this will still stay the same. This will be 44.2. And we still will have heat internal. The temperature will still be bigger, but not by as much. And we will have done more work on the system. We've now done 44 joules of work. Okay, well, how about 3 kilograms? Okay. Or 4 kilograms? And so on. We're continuously going to do more and more work. Now, will that just go on to infinity? Or will there be a maximum? Well, let's take a look here. If I go up to 11 kilograms, then this will not spontaneously fall. So nothing will happen. There'll be no work done. The system won't change. We won't get to this state. So I can't keep raising this up and getting work done because the system can only do 220, the system only has a 10 kilogram mass to fall, so it can't lift an 11 kilogram mass. Well, what if we do this? What if we do 9.9999 kilograms, right? Or 99999 kilograms. Well, what's going to happen here? This will still spontaneously fall. There will be just the slightest difference in weight, and that will fall. And if we were to put just a little bit more weight back onto this bucket, into this bucket, the system would go the other way. So if we add just a little bit more, the system will go the other way. And so this is just infinitely slowly falling down here, and we can reverse the direction with just putting a little bit more mass on here. And so what we call this particular case a reversible process. So it's a little different. It's the limit of those spontaneous process to where it's just about to stop and then no longer be spontaneous anymore. So we said 11 kilograms, that would not be a spontaneous process. Here, because this is essentially 10 kilograms, they're equal. So we take just a little bit off, we'll go spontaneously down. We put a little bit back on, we'll go spontaneously up. That's a reversible process. Well, let's look at the work under these conditions. The work is going to be 9.999 kilograms times 9.8 times the 1.5, which for all intents and purposes is 221.5 or whatever we had before. 221 joules. And so this work is exactly the change in energy that occurred in the system. This work we call work reversible, and we call that work max. So the maximum amount of work that we can get out of this system is one in which these are even. That leaves no impact here. So it just infinitely slowly goes to the ground. There's no impact with the ground. There's no dissipation of heat into this system. And so here, the temperature Q internal equals 0. So the temperature T2 is going to be equal to T1. All the energy has been extracted as work, and none of it goes into heating up this internal system. All right. So that's an adiabatic system, and in particular, it helps us understand this idea of maximum work. Now, maximum work doesn't have to be in an adiabatic system. It was most kind of easily seen here. But whenever we have a reversible type process, where we're just able to supply enough force that we need and not any extra force, then that will be a reversible process. All right, let's look at another type of system. This is called the closed system, and it doesn't really make too much sense why it's closed right now, but this will make sense after we have systems with a lot of particles and where we can lose or gain particles. Here the system is intact. None of the molecules of this ball are going off, and so that's why it's called a closed system. So what we have lost here now is this insulating chamber. It's free to just be anywhere, it's totally exposed to the environment. So what happens here now, this is teetering here. It will spontaneously fall, right? Because this is 10 kilograms and this is 1 kilogram. So we'll end up down here, just like before. But the heat energy will be dissipated off in all directions out into the environment. And so we will no longer call this heat stuck internal to the environment like it was here. It will go external to the environment. And in that case, the system will remain at its same temperature, even though it was a process like this first one in which the temperature raised. That was because the heat was trapped inside. Now the heat is free to go, and the system is just the same temperature as the surroundings before and after the state. All right, so that's a closed system. That's this idea of maximum work. So if we were to bring this up to 99.999 kilograms again, in this closed system, that would just barely tip, just providing enough force to lift that bucket in a reversible way. And so again, that would be reversible. So again, reversible is not stuck to adiabatic system. Closed system works as well. Not in an isolated system, because if by definition it's isolated, it can't do any work external to itself. You could talk about work done inside, but that's internal to the system. All right, so this is a more nuanced version of work. You won't see this in the chemistry book, your general chemistry book, or your general physics book, but it does lay the groundwork for some of the stuff that we'll be talking about in terms of thermodynamics.